Hello all, let's talk about free fall. Let me put these notes up here. Free fall is the motion of an object subject only to the influence of gravity. When near the surface of the earth, this acceleration due to gravity, we call it g, little g, is considered constant. The value we'll use is 9.81 meters per second squared. Now, free fall, or thinking only of gravity acting on the object, thinking of gravity as a force that creates this change in motion, this acceleration, we could derive various formulas. Basically, the formulas will tell us how fast the object is going and how far the object has traveled. For example, if we drop some rocks off of a high cliff, we could use these formulas to give a good estimate of how fast the object is going at a later time and how far it has fallen. Now, here are the formulas that are useful if you start from rest. If we simply drop an object, it starts from rest. Once we let go of it, the force of gravity acts and accelerates the object at a rate of 9.81 meters per second each and every second. So the very first formula here, V equals gt, this will tell you how fast it's going at a later time, and this is linear. The next formula, x equals 1/2 gt squared, well, that is distance as a function of time, and that's that quadratic. This comes from the world line. Remember the world line? X equals x naught plus v naught t plus 1/2 at squared. Well, that's the world line, but some of the terms have canceled out because we're starting from rest. The position we could let equal 0, and the initial velocity 0. So you get these simplified formulas. You could also write the distance traveled as v average times the time. And another one for how fast, there's a formula, a time-independent formula we can use to derive this square root of 2gx. This is very popular. You could think of x as the height, and if you knew the height that you dropped the object, you could simply calculate, knowing that in meters and using g as 9.81 meters per second squared, you could calculate the speed at the bottom of say, the cliff, if you knew the height of the cliff right before it hits. So, once again, this last formula here, the distance traveled, is always the average velocity multiplied by the time. If you watched a few of those other videos I mentioned, when you're comparing instantaneous velocity or instantaneous speed with average speed for the same time interval, you will find a relatively surprising result. You will find that the instantaneous speed or instantaneous velocity is double the average for the same time interval. So that is a useful concept to know, and we'll come back to that occasionally. But it is true, the distance traveled is always the average velocity multiplied by the time. All right, here are those simplified equations. If I put in 10 for g, they become very simplified. The speed would be 10t, and the position or distance would be 5t squared. So you could ask these questions: how fast, how far? You could also ask the question, how long does it take? These are typical kinematic questions. In fact, if we go back, let's just go back a slide if we can. This formula right here, if you solve this for the time, the x equals 1/2 gt squared, what formula would you get? Well, wouldn't you get a square root? Wouldn't you get t equals the square root of 2x divided by g? Think about that. In fact, that would be the time of fall. If you knew the height that it had fallen, or the distance, you could calculate the time of fall. All right, let's go back to this screen here. Oh yes, here is just a small sample of how g varies from location to location. We're going to use the worldwide average of 9.81 meters per second squared. That's good enough for us at this point. For simple calculations, we'll use 10. And here's a diagram of somebody throwing an object up. Notice what the speed or the velocity is right at the top. V equals 0. This is where the speed is 0. It's where the velocity is changing direction. On the way up, you could say it's positive. On the way down, it's negative. Now, the acceleration due to gravity is always downward towards the center of the Earth. And it's not zero at the top. Through the whole motion of this object, it's falling. And the acceleration is 9.81 meters per second squared, near the surface of the Earth. We're assuming we're staying near the surface of the Earth to use that value. If we get too far away from the surface of the Earth, the acceleration of gravity would be less. If you look over at this picture of the cliff, even though it's showing that this object was thrown up, once it leaves the person's hand, it is in free fall. It will slow down, be momentarily at zero, v equals 0 at the top. However, the acceleration is not 0. What is it? It's 9.81 meters per second squared downward. Or if you define up as positive and down as negative, you could say negative 9.81 meters per second squared. But these are both an example of free fall motion when you're just looking at the influence of gravity. We're assuming that the air resistance is negligible. And you can do that in many cases. Here's another example of our graphic of how fast it's going after so many seconds and how far it has traveled. Notice this is the linear relationship, v equals gt, and this is the quadratic relationship, x equals 1/2 gt squared. Notice how the numbers compare. If we use g as 10, then after 1 second it'd be going 10 meters per second, then 20 meters per second, then 30, then 40. And over here the distance fallen after 1 second would be approximately 5 meters, then 20 meters, then 45 meters, then 80 meters approximately. But if you want more detail, just use the 9.81, a more technical answer. But you can understand this just using 10. Now here is a position versus time graph of this type of motion. And notice it starts off with an initial velocity of 29.4 meters per second. If there's no air resistance, the final velocity will equal the initial velocity in magnitude. So the speeds will be equal, but the negative here is to indicate that it's on the way down. So this would be a velocity on the way up, and this is the velocity on the way down. That's what the positive and negatives are about, showing the direction. In this case, you have speed plus direction. Notice how the speed decreases on the way up. It's momentarily 0 and then increases on the way down. But it does this at a regular rate. And here are some graphs that represent this motion. This is the velocity versus time graph of this situation. Notice that if you started here at, I believe it was 29, let's look back, 29.4, let's just round that to 30. If you start at 30 right here, now this would be rising, and at momentarily you're at 0, and then this would be the falling. This is a very similar graph. When I ask you to graph bouncing, you'd have this rising and falling. Now, how do I know this is rising? Well, if I look up here at position versus time, this represents the rising in position, and then this represents the falling. But in the velocity versus time graph, even though I'm going on a negative slope here, this actually is the rising, and because the velocity decreases to 0 right here at the top, and then it increases in the other direction, so that right here would be the plus 30, and over here would be the minus 30. So be careful with this. These can be very tricky to read. We're rising and then falling. So this is rising, and then at this point it's falling. This is where it changes direction. However, if you look down here, acceleration versus time, the acceleration is constant. Notice it's in the negative, on the negative side here. Here's 0, this positive, 0, and negative. Just like here, positive, 0, negative. It's on the negative side. That means that the acceleration is negative. Well, we could say negative 10 meters per second squared. Take a look at these graphs, study these graphs, very important. And if you didn't do that bouncing exercise, you should look at this, because this actually will give you a great hint of how that graph should look. You should get like a sawtooth graph where you could do it many different ways, but you should have something like this where one part represents falling, the other part represents rising, and then the bouncing, you'll have a really steep really steep curve. To get back to the beginning here, you have a very steep curve because the acceleration is different when it hits the floor. It's more than just 10 meters per second squared downward. It's enormous. It's a very small impact time. So the forces are enormous and the acceleration will be enormous. So you get a very steep line and then you get the sawtooth again, then a very steep line and the sawtooth. So the transitions for the bouncing are very steep, whereas the falling and rising are this single line joined by where it hits the axis here, where the velocity is zero, where it hits the t-axis. We could call, instead of the x-intercept, we call this the t-intercept. So you could have something like this: rising, falling, bounce, rising, falling, bounce, rising, falling. So please try to draw a picture of that if you haven't already done so. If we want to describe free fall, of course, we could use a coordinate system. Up could be positive, down's negative. We could use the ground, the floor, wherever we want to put our initial position. A lot of times you put it on the ground. Depends on if you're initially throwing it up or you're dropping it. Remember, they're both cases of free fall. I like this setup. I like making it up positive, down, negative. And the acceleration will always be negative g, or negative 9.81 meters per second squared. The negative is the way we show downward in the math. The velocity, well, we use one of those Fab 5 equations. We'll use v equals v naught plus at, but a is negative g in this case, so we'll plug it in. And then our world line, instead of using x, because we're typically using x equals x naught plus v naught t plus 1/2 at squared. Well, now we can use y for our position. This represents position along the vertical axis. So initial position final position equals initial position plus initial velocity times time minus 1/2 gt squared. The acceleration is negative, so you just substitute in the world line. Position as a function of time, and you get this handy dandy equation. This is usually what you're going to solve right here with the help of the other four. So we're going to toss a ball. Toss it up. Leave your hand at 1.5 meters above the ground. It's moving at 7.3 meters per second. When does it hit the ground? Well, if you take y equals 0 at the ground level, which you can, it's up to you. The initial y will be 1.5 meters. And the initial velocity plus 7.3 meters per second. Making up positive is going to make the velocity positive. So the equation of motion for the position, the vertical position, we'll use y equals y naught plus v naught t minus 1/2 gt squared. And we know these values, we know what g is. We know what the initial position is. We also know what the final position is going to be. What's the final position? Well, the ground, right? We need to solve t when y equals 0. We want to know, when does it hit the ground? Let's do that. Well, we do the math. It is a quadratic formula when we do this. It's like solving for the roots. And when we do this, put in 0 for y. And we look at the equation. Once we get the numbers in, it follows the standard form. Ax squared plus bx plus c equals 0. And we can use the quadratic formula to solve for x. Remember, the quadratic formula is the opposite of b, plus or minus square root of b squared minus 4ac over 2a. We will get two values here, and those values will represent the time. Now you might ask, what does that mean? Why are we getting 2 times for this? Well, let's look at this situation. Let's put in the numbers. We put in the numbers, and you can do that on your own. The times come out to be negative 0.18 seconds and also 1.7 seconds. Which one do you think is correct? Or are they both correct? Well, give you a little history. There was a famous scientist known as Dirac, Paul Dirac. He came up with these strange answers when he was doing his derivations, and he realized that he didn't throw away these answers. He realized they had meaning. And in fact, he came up with the idea of antimatter. He actually received a Nobel Prize for this. So don't throw away your answers, even though they don't initially make any sense. They may have physical meaning. So here it is. Here's the position versus time graph, the world line. And this represents right here where it was thrown. It goes up and then it falls down. But notice this graph, if we extend it before the throw, it would also hit the time axis. So this is the time we're getting. We're getting the time before we threw it, as if we threw it from the ground level. The math doesn't know. It includes the past, the present, and the future. It predicts where it'll be in the future, and it also will make this prediction of where it was in the past. So it's interesting how this world line works. The math is like a time machine. It doesn't care about past, present, and future. It's in there. It works it out as if it was thrown from an earlier point. But we launch it at t equals 0. If it was launched at t equals negative 0.18 seconds in this position, the ground level, it would follow this path, pass through here where we have t equals 0, where we originally threw it, and land at 1.7 seconds. So that's what the extra time means. We would discard this time in this case because we want the positive time, the time in the future. All right, there's lots of experiments you can look up on Galileo and his, he would roll balls down inclines. He wanted to slow down free fall. He wanted to slow down the effect of gravity so he could observe it and measure it. And this actually represents a clock. You could actually use it as a clock, believe it or not. This is something else that, rumors has it he dropped, spheres from the Leaning Tower of Pisa and did experiments on free fall and determined, the acceleration was the same for all masses, which was surprising.